Hey guys, we're going to continue to explore lesson 7.5, and the title is kind of a misnomer because it kind of sounds like the last one. It's just called Exponential Functions, but we're actually going to go through some examples or applications of it. Exponential Functions. So yesterday we talked about growth and decay, and so we're going to kind of see some growth and decay in person. So we're going to actually take really short notes today because we're going to do another component with the applications in class together. So that's what we have to look forward to. All right, so we're going to talk about a linear function versus a exponential function. So linear functions versus exponential functions. So I'm going to start with a linear function. So we talked about those a lot. And it would look something if we created a table of values. Oops, that was supposed to be a y. That looks better. So we got 1, 2, 3, 4, 5. And we're going to have 1, 2, 3, 4, 5 pairs together. So our x is 0, 1, 2, -1, -2, and then we have 1, 3, 5, -1, -3. So basically what we're going to be looking for is how things change from one ordered pair to the next. Okay, so I'm going to look at the top here. To get from 0 to 1, I would add 1. To get from 1 to 2, I would add 1. To get from 2 to -1, I would subtract 3. To get from -1 to -2, I would subtract 1. Now, that doesn't look real constant, does it? Okay, so let's go look at the denominators. And to get from 1 to 3, I would add 2. To get from 3 to 5, I would add 2. Oof, look at this. To get from 5 all the way to -1, I'd have to subtract 6. To get from -1 to -3, I'd have to subtract 2. So I'm going to take all of those guys and I'm going to put them out together and I'm going to see what I can find. So we have 1, 2, 3, 4, 5 that we need to see. And the numerators in order were 1, 1, -3. Oops. Actually, we just need 4 of those. Sorry, have 1 too many. Let's get rid of this guy. And then we had a -1. And then in the denominators corresponding, we had a 2, a 2, a -3, a -2. Okay, so wait a second. I think we can, these two we could simplify. So let's take care of that. So let's see, a -3 and a -6. Let's see, they have a -3 in common. So it's going to give me a 1 over a 2. Oh, that's interesting. And then a -1 over a -2. Two negatives make a positive, so we get a 1 over a 2. So what we notice here is that we have a constant rate of change. So even though the numbers weren't identical, when I put them into ratios, then they ended up being the same exact ratio. So this is like saying they would all have the same slope, okay? So how do we figure out slope? Slope is going to be the difference in your y's. The delta symbol from Greek means change. So difference of over the difference in your x's. So for us, that's going to be the 2 over the 1, which is going to simplify down to a rate of change of 2. So the slope is 2. So that's what you're going to get with linear functions, okay? So it's a constant rate of change from one ordered pair to the next. So that's how they form a line. All right, let's look at our next one, which would be the exponential function. How does it differ from a linear function? So let's see, we got the same sort of idea. See if I can spread these out a little bit better. We've got x, we've got y, and then we're going to go 1, 2, 3, 4, 5. Okay, so x's we have 0, 5, 10, 15, 20. Ooh, we actually have one more grouping here. One a little further. 25. And then we have, for the y values, corresponding y values, 64, 32, 16, 8, 4, and 2. Okay, so let's look again at our constant rate of change. So I'm going to do, let's see. So from here to here, I'm increasing by a 5. I'm increasing by a 5, increasing by a 5, increasing by a 5, increasing by a 5. So that looks pretty constant, okay? So my x's are all constant rate of change. Let's look at my y's and see what we get here. So this would be subtracting 32. This would be subtracting 16. So as soon as I see that what's happening is the differences are not the same, right here, differences not the same, then that means the pattern isn't like an arithmetic sequence. It's not counting by the same amount every time. It's not going to give me that constant rate of change. So what I'm going to have to do is kind of come up with a different game plan. So let's see if I can think of something else that might work. Okay, so how can I get from 64 to 32? Okay, well, I'm decreasing, so that could be a division problem. So I could say it's dividing, and it would be dividing by 2. Or I could say that I'm multiplying by 1/2. Okay? Oh, let me make that a little bigger. So to get from 32 to 16, same thing, either dividing by 2 or multiplying by 1/2. And that pattern continues. Multiplying by 1/2, multiply 8 by 1/2 to get to 4, multiply 4 by 1/2 to get to 2. Okay, so this half is called a common factor. Okay, and so anytime I have this idea of a factor, a common factor, now I'm talking about an exponential function. There we go. So going back up to this top part here is that with this exponential function, I don't have an adding or subtracting pattern that's eventually going to simplify down to the same exact pattern. So what this is called is a geometric, so geometric sequence. And a geometric sequence is, it has a pattern that uses multiplication or division. Now you might say, well, it used adding on one part and it used multiplying or dividing on the second part. As soon as it involves any kind of multiplying or dividing, it is now a geometric sequence, and geometric sequences are what we need for an exponential function. Okay, so on the part that we're going to work on together in class, I'm going to give you a little front loading. So we're going to talk about applications. So you're going to have to look at data that's given to you, and you're going to have to determine whether it's a linear function or an exponential function. So you're going to be looking for a pattern. Now here comes the good news. Number one, the equation is going to be given to you. So you don't have to figure it out in most of these problems. Now you may have to substitute some numbers into it, and here comes another two. You need to use a scientific calculator. Calculator for final answer. Now it's going to be interesting because with our exponential functions, the x is the exponent on the numerical base. You guys are going to need to use a special key on the calculator. And the special key you're going to use is y to the x power. So what that means is I'm going to put in the base, that's your y, and then I'm going to hit the button, and then I'm going to use the exponent is going to go in. Now, where can you get yourself a scientific calculator? Your phone has scientific calculator. Desmos, you can use this as a scientific calculator. And you can buy yourself from the store. You can get a Texas Instrument TI. I like the 30 or the 36. Some of them say X. They're usually really, really good calculators and super cheap, like usually under $15. If more than that, under 20, okay? So, what am I talking about here? So, I'm going to go over to the right side, and let's say that you've worked out a problem, and you've gotten to this point where it's 3 times 1.25 to the 5th power. Okay, so we're going to follow order of operations. So anything with an exponent is going to get done first. So the 1.25 is going to be the y value, the base value, right? And the 5, so we'll give them a different color. 5, that's going to be the x part. Okay, so I'll demonstrate this with my calculator in class, and you'll see that. Okay, and then in class, we will go ahead and do a couple application problems together. All right, we'll see you then. Bye now.